So it's my pleasure to introduce Guido Tack. He's an associate professor here at Monash in the Optimisation group, and he's going to give a promised non-technical talk about how to make optimal decisions. So I look forward to hearing what he has to talk about. Take it away, Guido.
Thanks, Peter. It's mostly non-technical. There's a few technical things, but I think I'll try and describe them at a reasonably high level. So I think everyone will be able to follow. So like the title of the talk is how to make optimal decisions that are unfair, biased, and non-objective. I mean, obviously, it's really about the opposite, right? I mean, I'm going to show you that in many cases, this is what's going to happen if we don't pay attention, right? So we will make optimal decisions that are unfair, biased, and non-objective. And then hopefully I'll also talk about how to avoid that. All right, so I want to start with just a simple problem, right? It's 1962. You're a matchmaker. Your task is to pair up a group of men and women such that all the resulting marriages are stable. It's a classic problem. I'm sure some of you have heard of this problem before. So what does it mean for a marriage to be stable? It means, for example, if Bob would prefer to be married to Barbara over his own wife, Doris, but Barbara prefers her own husband, Adam, over Bob, then that's what stable means, right? So they don't have an incentive to break up their marriages. If this is true for all pairs of people, then everything is stable and all the marriages will stay like that forever, right? Till death do us part and so on. Okay, so life is simple, right? Very nice. This obviously looks weird, especially nowadays, right? Talking about these kinds of matchmaking. Anyway, just bear with me, right? It'll make sense in a few minutes, I hope. So why I'm telling this story and why I'm saying it's 1962 is because Gale and Shapley wrote this absolutely seminal paper in 1962 with the title College Admissions and the Stability of Marriage. And in this paper, they basically describe an algorithm, so a series of steps how to solve the problem, right? And this is how they say, to solve this problem, for each man, you select the woman he prefers the most and where you haven't matched them up yet. And then if that woman doesn't have a match yet, you match them up. If she already has a match, but she would prefer this man, then you change the matching. But if she would prefer to stay with her current match, then you keep everything as it is. And then you just repeat that until either everybody has a match or you've tried everything and you have to give up. Right? Very simple algorithm. And yeah, this was done in 1962. So let's have a look at how this works in practice. All right, so here's a table of potential matchings and their ranks. I think I'm going to try and use my mouse cursor to show you what I mean. So for example, in the first table here, that's how the men rank the women. And the second table is how the women rank the men. So for example, Adam ranks Barbara number 1, right? So that's his absolutely preferred match. And then second is Claire, Elsie is number 3, and so on. And we have the same kind of matching, same kind of ranking in the other direction. So for example, Doris would most prefer to be married to Adam and least prefer to be married to Edgar, right? That's how this table works. Okay, so let's try out the algorithm and let's see what the result is. Right, so we do this in several rounds. Okay, so round 1. We start with Adam. We match Adam with his preferred match, Barbara. But Barbara doesn't have a match yet, so we just pair them up, and that's our result for round 1. Continue with Bob. Well, Bob would also like to be matched to Barbara. So now we have to resolve that conflict. How do we do that? We look at the second table where we see, okay, Barbara would actually prefer Adam, her current match, over Bob. Right? Adam is rank 3, Bob is rank 5. So we basically leave everything as it is. Right? Bob misses out in this round. Next round, Charlie is matched to Elsie, right? Because Elsie doesn't have a match yet, and it's his preferred match. Dave to Alice, and Doris to Edgar. And that finishes round 1. So now in round 2, we have to go back to Bob, right? Because we don't have a match for him yet. So now we continue with his second preferred match, Doris. Now Doris also is already matched, in this case, to Edgar. So we look at the other table again. Doris would actually prefer to be matched to Bob compared to Edgar, right? Bob is rank 4, Edgar is rank 5, so we swap. right? So Doris is now matched to Bob because she prefers him, and Edgar misses out. So that leaves Edgar single, and we go to his second preference, which is Claire, who's unmatched, and we're done. Right? We found a match for everyone. I can basically transfer the matches to the other table now so that we can see like which woman is matched to which man and so on. All right, so that's the algorithm, right? Very simple algorithm from 1962. So now what we can do is we can analyze this, right? We can see what kind of result this is actually producing, right? And it'll become clear in a minute why it's interesting to look at that, right? So what do we actually want from an algorithm, right? What kind of outcome do we want from this? But first of all, we would like to know whether this is correct, right? The good news is, yes, this is correct, right? We can prove mathematically that this will always give us a stable matching if one exists, right? So the preferences could be given in a way that we can't find any stable matchings, right? And then the algorithm would basically say no. But if there is one, it'll always find one. Second question, is it fast? Right, that's also important, right? If we want to do this for a large group of people, then it has to be kind of fast. And it's reasonably fast, right? So roughly speaking, for 5 people, we have to do at most like roughly 25 steps, 5 times 5. For 10 people, 100. For 100 people, 10,000 and so on. But that's okay, right? That will work for reasonably large groups on a computer. Next question, does it produce good solutions? Yes, the solutions are optimal. They're guaranteed to match the highest possible ranks. Great news. Can you cheat? No, another really important point, right? The best option here is to give you truthful preferences. This is really important for these kinds of algorithms, right? You can compare it with kind of voting systems, right? If you have first past the post voting, like in the UK or somewhere like that, you may have to vote strategically, right? Maybe you prefer the smaller party, but that's basically wasting your vote because they have no chance of getting the seat anyway. So you go with another party just to make your vote count. So you have to vote strategically. In this case, you don't have to, right? You give your truthful preferences and you can be guaranteed that you get the best possible outcome. That's nice. So what happens when you design an algorithm like that? Get a Nobel Prize in economics, right? So it's a really influential paper. You can see that. So Shapley got the Nobel Prize in economics in 2012. Gale had already passed away a few years earlier, and because Nobel Prizes are not given posthumously, he unfortunately missed out on that great honor. All right, now I may have omitted a small important detail here, right? It's 1962. So usually, for a given set of preferences, there's more than one stable matching. And the results I just showed you only hold for the men, right? Only the men get their optimal match. Actually, the women get the worst possible match, right? That's kind of important when you analyze this algorithm, right? So you can guarantee optimality for one group, and you can guarantee the worst possible outcome for the other. You still get a Nobel Prize for that result, right? It's interesting. So the other thing is that women can actually improve their bad outcomes by misrepresenting their preferences, right? They can try and give their preferences strategically, right? They say, okay, I would actually prefer this guy in first as my first preference, but I'm probably not going to get him, so I put someone else first to improve my chances and things like that. That's always bad in situations like this, right? Because then if everybody does that, you may end up with an outcome that's actually worse than the outcome you could get if everybody had given their true preferences. And the women can also collude in this case, so they can form groups and vote strategically together and improve the outcome of the group and things. So it's terrible, right? It's really pretty bad. And the reason is very simple, right? We can look at the algorithm and we can determine, well, the men get to choose first, and that's why, right? So if you turn the things around, if you just say, okay, the women get the first pick, of course, all of the results are exactly the opposite way around, right? The algorithm doesn't know whether one group is men and the other one women, obviously, right? This bias in the algorithm is hard-coded into the algorithm. And of course, Gale and Shapley absolutely knew this, right? They discussed this in detail in the paper, and they never meant this algorithm as an actual solution to this problem, right? They didn't design the algorithm as a solution to this particular problem. They gave it as a thought experiment or as an example for this type of algorithm. right? Okay, so what about 2024? Can we do better, right? Can we actually achieve fairness in these kinds of problems? Well, first of all, the bad news is when you just Google for this, it's terrible. You get like articles like this, Gale-Shapley, the algorithm for love, which says, why is this algorithm so powerful? Well, it ensures that everybody ends up with the best possible match. No, actually it doesn't, right? It actually does the opposite. So yeah, bit of misinformation there. Also, I found this one from a few years ago about apparently Hinge was or is a dating app. I don't know about that kind of stuff, but the heading is, well, this is how the Nobel Prize winning Hinge algorithm actually works. Well, the Hinge algorithm definitely didn't win the Nobel Prize. And if they implemented Gale-Shapley as the algorithm in Hinge, I know one group of people who shouldn't be using it. Right? It's interesting. I mean, I'm sure that's not what's happening there, right? But clearly, yeah, there's a lot of misinformation around these types of things online. All right, but why is this important? Well, these kinds of problems are absolutely everywhere, right? Matching problems are very, very common, or matching allocation problems. So things like allocating teachers to classes, or like staff to customers, nurses to shifts, students to universities, donated organs to patients, foreign aid to people in need. Right? There's tons of applications for allocation or matching algorithms. Right. So can we do better? How do we solve these kinds of problems with the technology that we have? And can we achieve fairness? So I want to show you a couple of examples using MiniZinc. Now, I know that most of you probably have a rough idea what MiniZinc is, but it's a modeling system that we developed here at Monash with support from Optima. And I'll just show you some examples. Like if you've never seen it before, you don't have to really understand the details, but I think it'll become clear what I wanted to show you with this. Okay, so what I'm going to show you is basically how we can write down this problem, the stable marriage problem in MiniZinc. All right. So I don't usually type this fast. This is sped up a little bit. But what we do is we basically set up some input data. So we say, okay, this is how the men rank the women. This is how the women rank the men, and so on. And then we have two important components here that are mapping the men to their wives and the women to their husbands, right? So that's kind of the output that we're trying to achieve. And then we put these constraints into the problem, right? So we say constraint, don't worry about this one first, but the second one is interesting, right? We say for all men and for all women, we give the men a name M, the women a name W. And then we say, well, if M ranks the woman W better, right, lower rank, then he ranks his own wife, then W ranks her husband better than M. And that's exactly what we said what stability means, right? So basically, we simply state the rules of the problem here, right? It's not exactly just English, but it's close enough, right? We can be sure that this is exactly the rule that we wanted, right? We can just write it down, and we know that we've specified the problem that we want to solve. So that's the nice thing about these high-level optimization languages like MiniZinc, that you just declare what your problem is, right? And what you can notice here is that we don't say anything about who gets to pick first, right? We don't say the men get the first pick or the women get the first pick or anything like that, right? There's no bias in the model, right? We don't say who's the preferred group in this situation. All right, so I've copied in the actual example that we saw, basically exactly as it was on the slides. And then we just click the run button, and in a few milliseconds, we get a solution, right? And the system then tells us, okay, for example, Adam is matched with Barbara, Bob with Doris, and so on. Right, so I've transferred that solution onto this slide. Maybe it looks a bit familiar, right? This is exactly the same solution we got from Gale-Shapley, right? So we can compute, for example, the average rank that the men get. It's 1.4 in this case. The average rank that the women get is 3.2. right? So clearly, it's doing exactly the same thing. Why, right? Where does that bias come from? Right? We didn't say anything about the men getting to choose first, right? Why did they still get their first choice? Well, maybe because we wrote the rule just in one direction, right? We just said like the ranked men and so on. So what about that one? Well, let's just try that out. Let's just write the rule down the other way as well, right? So we just turn it around. We start with the women and then the men, and just say, okay, if the woman W ranks the man M higher than her husband, then M ranks his wife higher than W, right? It's just the opposite of the rule. So maybe that helps, right? Because maybe we just forgot to put that rule in. Okay, what happens? Well, we get a slightly different solution. You might not be able to see it here, but I'll just put it on the slide here. That's the difference. Okay, so we get basically two people swapping their partners here. We do get a different outcome, right? So the average rank for the men is now 2.2. The average rank for the women is 2.6. So it's a bit closer together. So maybe this did actually help. There was another part in the model where it's not symmetric. And that's here in this constraint that I didn't talk about earlier. So let me just replace that one with the opposite version and see if we still get a relatively balanced outcome, right? Just to make sure that we didn't just accidentally get this result. Okay, so I'm basically just turning that constraint around. That's fine. It's basically meaning the same thing. Remove the other one. Get a pretty different solution this time, which looks like this. So suddenly the women get 1.2. All of the women except one get their first preference, and the men get only their fourth preference. So what's going on, right? It seems completely random what's happening here. Okay, but the critical thing is all of these solutions are stable, right? So all of the solutions meet that main criteria that they're stable, because that's in the constraints, right? We can't violate that rule. So basically, if we look at this, we can choose between a solution where the men get their first pick and the women are trapped in stable but unhappy marriages, or the other way around. Okay, not ideal. So what do we learn from this? Well, the first point is that old school algorithms like Gale-Shapley may be inherently biased, right? It's hard-coded into the algorithm. But we can analyze them and then explain exactly what kind of bias they produce, right? We can use all the tricks from algorithm analysis and design to do that. Modern algorithms, like the optimization tools that I've been using here, can also introduce bias, but it's completely hidden, right? The model may look harmless, but the results can be just as bad or worse. Actually, I think the results are worse because we can't analyze or prove anything, but we don't even know what the results are going to look like. We may get a reasonably balanced result 9 out of 10 times, and then the 10th time it's just awful, right? We don't know. It can be completely random. It may change with subtle edits to the model, like we just saw, or software updates or things like that, right? It's completely outside of our control. Okay, where does that leave us, right? What's my point here? What do I want to get at here? But we can't achieve fairness by not talking about differences, right? That's just a fact. What we tried in the model was to just ignore fairness. We said, okay, if we don't mention that the men don't get the first pick, then everything should be fine. But that's obviously not true, right? We can't avoid that problem by just not talking about the differences there. So we have to actually tell the algorithm what a fair outcome looks like. But we have to make that explicit rather than just trying to avoid it or ignore it. Okay, so to do that, we have to decide what fairness actually means, right? We can't just hope for a fair outcome from an algorithm. We have to tell it what we mean by fair. And that's not easy. It's not obvious, and it's something you have to really understand in a lot of depth. Okay, let's go through a couple of examples. So I'm sure a lot of you have seen this kind of cartoon. It's a very nice way of distinguishing between different terms here. And the main thing that's really important is to distinguish between equality and equity. So, I mean, as you can see in the cartoon, right, we have some resources like the boxes that the people are standing on. And we have some outcomes. Like in this case, the outcome is to be able to watch that baseball game. So equality means that everybody gets the same resources, right? But in this case, it means not everybody gets the same outcome because one person here just can't look over the fence and basically doesn't have any outcome at all. In the second case, we redistribute the resources in a non-equal way, but the outcomes are equal. Everybody gets to see the game, right? So equity is often defined as equality of opportunity, and it may require inequality of resources or some other level of inequality. Right? So that's the first thing. We have to be really clear about what kind of equality or equity or fairness we want to achieve. Right? In this case, it's not so clear what we mean by equality or equity. The other distinction between fairness and equity is a bit more vague. I haven't really found any clear definitions. Some definitions say it's basically the same thing. Some say, well, fairness is more about the individual and equity is more about groups of people, but they're basically describing the same thing, right? It's about equality of opportunity or those sorts of concepts. All right, so when do we actually want equality, or what kind of equality do we want, and is it achievable? Well, let's look at stable matching again. In stable matching, equality would mean that everybody gets the same rank match, right? So for example, worst case, everybody gets their least favorite person as a match, but at least everyone's the same, right? That would be an equal outcome for the matching problem. Let's try that out, right? I can just add a constraint that says all the ranks have to be equal. I've added some code to make that a bit easier to write, but I can just basically say all equal for all ranks. Everybody gets the same rank. Computer says no, right? The result is unsatisfiable, which just means there is no solution, right? Given the preferences, there is no stable matching where everybody gets the same rank, not even everybody getting their least favorite person. So sometimes that's simply not possible, right? Sometimes it works if the preferences are just right, because the matching still has to be stable, but basically it means never, right? For realistic scenarios, we can forget about this. So I've got a few suggestions here about outcomes that could be considered fair, right? So what do you think? So for example, we could say that the matching is fair if the average rank is as good as possible, right? So on average, everybody gets a pretty good rank. That's one way we could define fairness. Another thing we could try and do is to minimize the difference between the best possible rank and the worst possible rank, right? To say, okay, like the extreme ranks shouldn't be that far apart, right? So maybe that gives us a bit more flexibility rather than saying everybody has to have the same rank, where we say, okay, you can have slight differences between people, but the difference shouldn't be too big. That could be another way of defining fairness. What about everyone has the same chance of getting their best match? Right? That could be another way of defining it. If we say, if we look at these cases, it's clear that not everybody can get their best match. Right? We know that it's not possible. But maybe we just have to make sure that everybody has the same like random chance to get the best match. What about everyone gets the best match they can without disadvantaging someone else? It's another interesting way of phrasing this, right? So as long as it doesn't matter for anyone else, you can get the best possible match. If we have recurring matchings, for example, like a monthly games night where you have to put groups of people together, or maybe everyone eventually gets their best match, right? Or the same number of times over the course of a year, or things like that, right? But we're now not solving a single problem, right? Each single problem can be extremely unequal, right? But over time, you get a fair outcome. So there's lots of different ways we can define this, right? Lots of different ways we can think about what fairness means, and it'll depend a lot on the concrete problem we want to solve, right? It's not the same solution for every kind of these problems. Okay, so how can we do this in optimization? How can we actually achieve this in practice? So I'm going to show you some simple examples first, and then go through a couple of examples that are a bit more complex, where we maybe need a bit more kind of machinery to think about what fairness means and how to represent it. Okay, let's talk about very simple metrics, right? We just want to measure how good our solution is, how fair our solution is, and then tell the solver, try to improve that as much as possible. So we can express fairness as an objective function, or some people call it a cost measure, or optimization goal, or loss function, or other things, right? It just tells the system how we measure whether a solution is good or not. And so based on the things we just discussed before, we could try and minimize the sum of all the ranks, right? Which is basically the same as minimizing the average, right? Because average would just be dividing that by the number of people. So it doesn't matter which of the two we minimize. So basically minimizing the average of the ranks. We could minimize the maximum rank. Now that would mean making sure that the worst off person gets the best possible match. Could minimize the difference between the best and the worst rank. Now that's another thing I said before. So let's try that out. Okay, so first idea. Well, this is just, I had to actually extend, let me just go back here. I had to extend the problem. So we're now talking about 6 people. There's Fred and Fiona have joined our groups, right? Because with 5 people, this just doesn't work out because all the solutions are the same. So I had to add another person in. All right, so for these 6 people now, let's see what happens if we just run the problem. It's pretty unequal, right? Somebody gets their first rank, you can see that here, right? The minimum rank is 1. Somebody gets only the 5th rank. The average is 3 and a third, right? And the men and the women have very different average ranks again, right? That's just if we don't do anything in particular. All right, so let's try and add one of these objective functions now, where we say we want to minimize the sum of all the ranks, which is basically minimizing the average rank. Well, the average rank is still 3 and a third. I think this is exactly the same solution we saw before, right? So accidentally, the system already produces the solution that has the minimum average rank. We didn't tell it to do that, but now we can verify it's actually just doing that out of the box anyway. To be honest, I have no idea why, right? I didn't try and find out why. It's just a coincidence. All right, so what about the other options that we just went through? One of them was to minimize the maximum rank. And we can just write it down like that, right? Minimize the maximum over all ranks. Now, we can see a difference here. The maximum rank is now 4. So the person who previously was allocated rank 5 out of 6, right? Because we've got 6 people now. That person, well, or somebody else, now has rank 4 as the worst possible option. So we've kind of improved the overall situation. Right? There's still quite a bit of inequality there. The women still have a lower rank overall than the men, but not quite as extreme as before. Somebody still gets the first option, which may be fine, right? But that's what happens when we do the maximum. Now, the final thing I wanted to try here was to minimize the difference between the maximum and the minimum. Right? So this would mean that, okay, we can allow slight differences between people, but not too much. If we do that, well, the worst off person drops back to rank 5. The best one drops down to rank 3. Right? So instead of having somebody who gets their first preference, nobody gets a better preference than preference 3. And nobody gets a worse preference than 5. So the difference between those groups has shrunk, right? I'm not sure this is the good outcome for this problem, right? So it just means, again, all the marriages are stable. So we're locking everybody into kind of slightly below average marriages. No, not an ideal outcome, right? Again, like this was never meant to be used for marriages, obviously. Right? Right, but this has done what we asked it to do, right? It's compressed the range of options or the range of preferences. We could do all kinds of other things, right? We could say, well, we want to compress that, but also not have anyone have a rank worse than 4, right? We could just add more rules into the system and it would just happily do that for us. Okay, but now I want to talk about 3 people in a bit more detail. Who have done a bit more fundamental and a bit more theoretical research about how to measure inequality and how to produce maybe fair or just outcomes, right? So that this hopefully has a bit more substance than just trying to minimize the maximum, trying to minimize this and that, right? Okay, so and the 3 people I want to talk about are Corrado Gini, John Rawls, and John Nash. Now I have to say I'm not an expert in in this area in particular, but I think it has so much overlap with what I'm working on that it's important to at least know a little bit about this kind of background for optimization. All right, so the first person I want to start with is Corrado Gini. So he was an Italian statistician, demographer, sociologist, also a eugenicist and a fascist. So a bit of background there. And as often in the history of science, like terrible people have come up with great ideas that we still use today. His name is still attached to all these ideas. That's just how it is. So his claim to fame is measuring variance in basically groups of people. So if we look at the main thing that he's worked on, or the main thing he's famous for, the so-called Gini coefficient, it measures the inequality in income or wealth distribution in a population. So how does it work? Well, here's a graph where on the x-axis, we have kind of the share of the population, and on the y-axis, the share of the wealth in a society. And so in a totally equal society, the graph would look like this, right? So for example, 20% of the population, the bottom 20% of the population have 20% of the wealth, the bottom 50% of the population have 50% of the wealth, the bottom 70% have 70% of the wealth, which basically means that everybody has the same. That's the only way to make this work. All right, so what that means is if we draw a line here, which we call the line of equality at 45 degrees, right? Basically, that's a fully equal society at that line. And whenever we drop below that line, we have an unequal distribution of wealth. So for example, if we look at this distribution here, well, we have 50% of the population only having about maybe 23% of the wealth, which means that the other 50% of the population have 77% of the wealth, right? So you can see that the further we drop below that line, the more unequal the society becomes. And we can measure that by comparing the green and the blue areas in the graph, essentially, right? So the Gini coefficient is simply the ratio between those two areas, right? And so here's an even more unequal situation, right? Again, the green area is larger, the blue area is smaller. So the more green versus blue, the more unequal the society is. And we can use the same measure for all kinds of other things, right? It doesn't have to be wealth in a society or income or anything like that. It gives us basically a number between 0 and 1 that tells us how unequal this kind of distribution is. All right, mathematically, it's this formula here. We don't even have to really understand the details, because really what it is the sum of the differences between any pair of people divided by the average over all people, right? That's basically what it is, right? Plus, minus a few constants and so on. So that seems easy enough, right? So we can try that. We can just write that down. So if we do this in MiniZinc, I'll just basically define the differences between all the ranks here. So it's the absolute difference, right? So it doesn't matter which one is larger. Don't worry about the details. This is just computing the difference between all ranks, all pairs of ranks. And then I'm just saying, okay, minimize the sum of all those differences divided by the sum of all the ranks, which is basically the average. Right? It doesn't matter. The details don't matter here. If we do that, we get an interesting distribution. So we get the average actually equal between both groups at 3.5. We get 5 and 3 as the minimum maximum. We get this kind of distribution, right? 7 people get their rank 3, 4 people get rank 4, and 1 person gets rank 5. So it does produce a reasonably equal distribution, right? So this measure definitely does what it's supposed to do. All right, so what is a problem with this one? Division can be a bit tricky, right? I mean, I just wrote this down in MiniZinc, and the algorithm I chose can kind of handle it, and it works for this example. Some optimization algorithms may be able to deal with this in slightly better than others, but we've done some work on how to implement this, but it's a bit tricky, right? So you may have to work around some problems if you actually want to use this for large real-world optimization problems in practice. Okay, the next person I want to talk about is John Rawls. So John Rawls is probably one of the most influential political philosophers of the last century. passed away in 2002. And his main, most influential piece of work is A Theory of Justice, a book from 1971. And he kind of has this concept of justice as fairness. And his work is all in the context of just societies, how to build a society that has kind of justice and fairness built into the principles, into the institutions of the society. And all of this is based on what is called the original position. And the idea here is that you have to reach an agreement about how to run a society or how to run an institution without knowing which place in the society you will take once all of that is set up, right? You don't know whether you're going to be at the top or at the bottom. And then the logical conclusion from that is what is called the difference principle. It means that if that's your starting point, the only logical conclusion is to improve the welfare of the worst off in the society, because you could be the worst off in the society, right? This is really very roughly summarized, and I apologize to people who've studied this in a lot more detail. But I think it's kind of the essence of this position. It's important to understand that he applied this to how societies work, and he has kind of other aspects that have to be in place for this to make sense. For example, equal access to resources. Yeah, there's other concepts that have to be in place around this for this to make sense in a society. But in terms of solving optimization problems, we can kind of follow the same argument, right? We can say, okay, if we don't know which of these outcomes will be for us, then the best possible thing for us to do is to optimize for the worst off case, right? So that's something we can take away from this. Now, how does this look in optimization, the difference principle? How can we implement this? Well, we've already seen how to improve the outcome for the worst off, right? So we minimize the maximum rank, right? We try to get the worst off person to have the best possible ranking outcome in the matching problem. What about the second worst off, right? So all we've done is maybe improve the worst off from rank 6 to rank 5, but maybe we could also improve the second worst off from rank 4 to rank 3, right? We didn't tell the algorithm, and so from all we've learned, it's probably not done that, right? Because we didn't tell it to do it. So it may have improved the outcome for the worst off, but maybe the second worst off still has a pretty bad outcome, and we could do something about it. So how can we fix that? Well, we apply this principle recursively, right? We first improve the outcome for the worst off, then the outcome for the second worst off, then the outcome for the third worst off, all the way to the top, right? Even like if the best outcome in the original one was that the best person got rank 2, well, maybe they can get rank 1 without making anyone else worse off, right? And if that's the case, we should do it, right? We should try and improve the outcome for every single person in that group. Okay, there is a way to implement that. It makes things a bit more complicated, but we can actually write that down. So let's first of all count how many people are in each rank, right? So we just say, okay, for all ranks from 1 to n, how many people get assigned that rank partner? And then we minimize over all of those, and we multiply each of those counts by 10 to the power of I, essentially. So it means that for rank 6, we get a factor of 10 to the 6. For rank 5, we get a factor of 10 to the 5. For rank 4, a factor of 10 to the 4, right? So it means if we improve rank 6, we get a payoff of 10 to the 6, right? So we're not going to try and improve rank 5 before we've made sure that everyone at rank 6 can't get a better outcome, right? So it does exactly what we're trying to do, right? It first improves the worst off, then the second worst off, then the third worst off, and so on. If we do that, we actually get an interesting outcome here. So this is almost the opposite of the Gini outcome we saw before, right? We've actually spread people out a bit more. We've got now 7 people on rank 4. We've got 1 person on rank 1, which we didn't have before, right? This is a more unequal outcome, right? We've not improved the equality of the solution, but for each rank, we've improved how the worst off, basically, the position of the worst off in that rank. So it's a different way of looking at things, right? And I don't know if this is better for this particular application, right? It's completely application specific. If this is an industrial problem, is your industry customer going to like that outcome better than the Gini outcome? I don't know, right? We have to really analyze and understand what we want in terms of fairness and then implement that. All right, what's the next one? The final person I wanted to talk about is John Nash. So American mathematician, got the Nobel Prize in economics in 1994. Obviously, that's not John Nash. That's Russell Crowe playing John Nash in A Beautiful Mind. This is John Nash, and yeah, one of the most influential people in game theory. Right? So he's known for his incredible contributions to game theory, and so in game theory, what we're interested in is, well, this is from Wikipedia, strategic interactions among rational agents. Right? We have people interacting. We've got people who kind of change their mind based on what others are doing, and we want to kind of optimize an outcome in a way, but it's not the same thing as the kind of problems we've looked at before here. And the Nash equilibrium is what he's really famous for, and that kind of describes solutions, stable solutions of these games, where no one has an incentive to change what they are going to do. But again, this is not that related to what we've seen before, right? But he's also worked on something called the Nash bargaining solution. That's kind of his second most favorite thing he's done. And that is actually a measure of inequality. So this applies directly to what we've seen so far, right? We can apply this to situations that are not really games, right? We can use it to measure inequality. What does that look like? Actually, it's very simple, right? Again, if you don't like the formula, don't worry about it. What we have in the formula is what we call a default outcome, right? That's what everybody gets if we can't reach an agreement, right? So for example, nobody gets anything. That's a completely fair outcome, right? Completely equal outcome as well. Probably not the desired outcome, but it's a fallback solution. And it's a fallback solution that we can use to measure against, right? We can say, okay, for any outcome, how much better is it than our default position, right? Another default outcome could be, let's say we have things that we want to distribute among people, right? And certain people want certain things and not other things. So the default outcome could be everybody gets what nobody else wants, but they want, right? And nobody will be unhappy about that, right? If nobody wants the bottle of water that I've already had a sip from, well, I can have it, right? Nobody else will be unhappy about that outcome. So that could be another default outcome that we can fall back on. Okay, so we just pick a default outcome that everybody will be, well, not happy with, but at least not angry about. Okay, and then what we do is we multiply, well, we look at the difference of UI, which is what we get from the outcome of the problem. We look at how far away that is from the default outcome that we would get if we didn't do anything. And then we multiply all those values together, right? Instead of adding them up, we multiply them. That's the only difference really to some of the other things we've seen before. And this multiplication gives us what's called proportional fairness. So proportional fairness basically measures an area. So if we have here the outcomes for Alice and Adam, right? And maybe this is the default outcome that both get their fourth preference. But maybe we can find a solution where Adam gets the first preference and Alice the third, right? So that would give us this kind of area if we multiply those two values together, or those two differences. Maybe there's another solution where Adam gets outcome 3 and Alice gets outcome 2. So that's another solution where we can multiply those two together. And the Nash bargaining solution tries to find the outcome that maximizes that area, right? It just means any other solution leads to a loss for one of the players. So it's another way of measuring the fairness of a solution, and in this case, proportional fairness, because we're basically looking at these ratios of those areas there. We can add that to MiniZinc. This is, again, minimizing the sum over all ranks. So the previous one that we've done, just as a reminder, right, we got an outcome, maximum rank 4, minimum rank 1, and quite a bit of difference between the two groups. Now, all we have to do is, instead of summing the ranks up, we just have to do a product, right? Multiply all of them together. And if we do that, we get a different outcome. And this is interesting. We get an outcome where all the averages are the same, 2.2. That's actually not not too bad. The maximum rank is still 4, the minimum rank is still 1. Right, but this looks like a pretty good result actually compared to some of the earlier ones we've seen. So Nash bargaining solution is potentially an interesting way of measuring inequality in these situations. Again, I don't know if this is the appropriate one for this kind of problem, but it's one more tool in our toolbox that we can use. Now, again, why is this difficult? Because multiplication is difficult, right? The types of solvers that we typically use are not very happy with multiplying numbers. It worked in this case because I went back to the problem with only 5 people. I tried it with a 6 people solution and it doesn't work. It blows up, right? Because multiplication leads to large numbers and then things stop working. So there are ways around it. There are tricks you can do, but at least it's maybe not as straightforward to do it. All right, I'm running out of time. There's a lot of things that I would have liked to talk about. Lotteries. Lotteries are really interesting, right? That's something I mentioned earlier. What if we say, well, your chances of getting your first pick are the same for everyone? How can we achieve that, right? Maybe we can do that by somehow tweaking how the algorithms work to make sure that they really randomly pick those solutions. The other thing is achieving fair outcomes over time. And we've had, like Alex Eck, one of our students, previous students, did some work on that. And I think we need to pick that up again because it's obviously very interesting, right? Sometimes you can't get good outcomes for like a single shot problem, right? Where you've only got one chance, right? Somebody will lose and somebody will win. But over time, you can make up for that. So that could be really interesting. And then producing a diverse range of solutions and letting people vote, right? Maybe the preferences you get are preferences that you collected, well, when people didn't really know what the outcome would be, right? If you then show them a range of outcomes, maybe you get much better preferences, right? So there's lots of interesting things to develop here. And some of the challenges are, how can we balance efficiency and fairness? Like if we're trying to improve fairness, we almost always have solutions that have higher cost than if we didn't try to improve fairness, right? It's a trade-off. It's a balance where we have to really decide what is more important for us. How can we audit optimization models for fairness, right? Given a large model for a real industrial problem, how do we find out whether there's some hidden bias actually in the model that we're not sure about? How can we then convince people that the outcomes are indeed fair, right? How can we convince people to use our solutions if they're not convinced that the outcomes are fair, right? How can we elicit useful preferences? And then how can we solve these problems when they get really large? I mean, that's, as I just said, right? This worked for 5 people. It didn't work for 6, the Nash bargaining solution. Lots of interesting questions. Right, so the takeaway message really is that we simply cannot achieve fairness by not talking about differences. Right? We have to really model the fairness. We have to put it into our problems to say what we mean by a fair outcome. And what is considered fair is an interesting question. There's lots of options, and I don't think it's really, there's no clear winner here. Right? We have to make that decision for every single problem that we want to solve. And that's all I want to talk about. Thanks very much.